Very well. Hello, thanks for the not much of an introduction, but I'm from Grammatio Kohler Research. My name is Oliver Bucklin, postdoctoral researcher, and I lead the team for digital timber. What is Grammatio Kohler? It's the chair for digital fabrication and architecture, and it's inside of the Institute for Technology and Architecture at the ETH Zurich. This is a great image. I think it's very early. Mike here's one of the very first researchers in the Institute, and he's still there. He has now a leadership role in the lab. And the idea was, how do we combine humans and robots in construction for architecture? I think at the beginning there was a lot of use of industrial robots and the idea that we can just automate everything. And now we've taken much more of a human-based philosophy where we think humans are really necessary in most fabrication environments, including the most automated ones, like automobile factories are the clear example, where you still have people involved at almost every step in the production of cars. Obviously, buildings, as every building being a prototype, is even more necessary to have humans involved. As I mentioned, we're in timber. We love wood for its environmental benefits, as well as, for these personally, its aesthetic qualities, its thermal qualities. It has many positive attributes. But as a construction material in an industrialized setting, it is still, unfortunately, more expensive than massive construction. We're working on it, getting closer and closer to being cost competitive. This is mainly because of their complexity. They have more parts and they require more specialized knowledge to produce. There are fewer people who are trained in timber construction than in traditional steel or concrete or sort of standard modernist construction. Additionally, wood is a limited resource. We want more people using wood, but we want more people using wood better. So that means using it efficiently and not just emulating sort of massive construction techniques with wood. So our vision is sort of a second digital turn. It's to use timber because we like it. It's to take advantage of the fact that it's lightweight and already highly digitized. And through computational tools, then to reduce the complexity and the financial costs, the time costs of building with it. So I think we've seen various iterations of this diagram many times throughout the weekend. But the problem is there's different cultures. I think this is one of the biggest ones. We all have a different education. I was trained as an architect and a carpenter, but in a foreign context, say, to what we learn here in the DACH region. And that's different from engineers, from planners, from people working in the shop. Additionally, we have linear data flows, where we know the data gets lost at each of these transitions. And we have, obviously, really, really strong software in each of these realms, but everyone likes their particular software more than the next guys. And this leads to data silos where the software doesn't communicate very well with each other. We see this as an optimized or say idealized workflow where data flows freely, where information isn't lost. But this is a huge challenge, and I think there's several challenges this weekend that are addressing this in different ways. And now getting to the crux. This is where I present Compass Timber, the subject of today's presentation. And we're positioning Compass Timber sort of at the nexus of these disciplines to try and create this kind of glue that helps hold everything together. Maybe glue's not the best metaphor, maybe grease or conduit or something that helps things flow. So Compass Timber, it doesn't stand alone either. It's part of the Compass ecosystem. Compass is at its core, what we call a framework. Think a toolbox of various packages that are geared towards aiding in collaboration in AEC research and in the industry. It's an open source foundation as well. It's an association here in Switzerland, which means it's transparent in terms of the code. You can go and download it, change it, has a fairly permissive license as well. But it's also a social construct that is transparent in its conceptualization, meaning it's now a separate entity from the ETH. So it has its own leadership, and they determine sort of where the direction of it is without being based on sort of input. I mean, there's input, obviously, but direction from the ETH. So these are basically the core principles of Compass. It's open source, it's CAD agnostic. We interface with many different CAD programs, but it's not dependent on CAD programs. Data-centric, and I'll get into that in a minute, and then transparency relates both to the association and the code as open source. So through these packages, this entire ecosystem, we're able to do much more than we could do simply as the Compass Timber team. So there's packages for structural analysis, for robotic path planning, for 3D printing, for IFC generation. Lots of very complex packages there. So really, this is sort of our statement of intent, what we intend to do, provide a toolbox for planning automation and data exchange. I think those are the main concepts to hold in your mind. So data exchange, we have IFC. What's the problem? Why not just use that? I think we know that IFC is strong. It has its utility, but when it comes to how it's implemented, it's just really complex and not implemented consistently between different users of it. So it's primarily an export format, and then you read it in and base your model off of it instead of using it as a direct model. We have some ideas about how to still use IFC. It's quite universal, so it's not something we need to replace, but maybe something that we augment. And this is something that we're looking forward to looking into. Anyway, looking at this data exchange primarily, we are approaching this by developing a semantic model. A semantic model describes components primarily through their properties. This is where we get to the data-centric aspect of Compass and Compass Timber. So in this case, we have beams and joints. And yeah, we could put some meshes out there that describe this, but then you don't know what it is. It's just a shape in your screen, in your computer. So we ascribe attributes to them. We say these are the dimensions of the beam. This is where it is in space. And very crucially, what its relationship, what its role is in the building and what its relationship to its neighbors is. And it's really with these joints that we then add more information to these beams. So that means the joints are generating features, and we see features as not just, okay, this Boolean subtraction for this geometry. No, it's also CAM data. It can be information about manufacturing or additional fasteners or the structural characteristics of the joint. And then we're looking at, oh, did I have two there? Oh, right. We've also, it's in this goal of becoming more of an exchange format, we've tied it very closely to the BTLX format, which is a CAD agnostic, a machining agnostic machining format, as sort of idiosyncratic as that sounds, which is also turned out to be somewhat relevant for this challenge we're participating in. Right, but that same logic of two beams, they connect, they have a joint. The joint is what creates features and helps describe the characteristics. We're looking at this hierarchically to say building elements, or let's say parts, groups of parts can also interact with each other through joints and connections that then generate even more complex feature types. Right. So I think these are sort of core takeaways. The model uses a graph structure to describe the building parts and relationships. That's quite core to the Compass model, not just our version of it. And data is king. Data is really, or data is the reigning monarch. And that takes precedent over geometry because we know geometry can be imprecise, it can lose intent in many ways. So here's our data model. It's basically a JSON where we're able to add attributes as the building gets developed. And it describes then the parts, the relationships, and in a sort of hierarchical and consistent way. We have plenty of interesting exchange projects with partners. This is one that just wrapped up, which is using an augmented reality interface for construction in timber construction. This is an app. It's a startup that is a sort of ETH spinoff. Oops. Sorry. And it uses at the base some compass timber models. We're also looking at a project with CADWork and Erne to really push this exchange format. I think CADWork is a major player in the timber industry and the generator of the most common timber planning software in this region. It's really crucial that we work closely with them. So this is a project that just started and it's going to be pushing for this exchange of data between Revit and CADWork, so having robust workflows there. And finally, to test this planning automation, I'll jump into the planning automation side. We're now looking at a project in Ukraine where we will be pushing a lot of the automation processes. They have extreme worker shortage, obviously, because of the war, and they have an extreme housing shortage, also because of the war. So we're really glad to have a project there with locals where we're really hoping to implement a lot of our planning automations that maybe aren't quite ready for the sort of highly complex, Swiss technology, but that can hopefully make an impact there for more simplified and nevertheless robust and high quality architecture that we hope to begin implementing. Finally, I'll just show a project that we did. This shows a lot of the sort of start to finish workflows that we can do with Compass Timber, including the automations, these planning automations. We built in Dicentis Muster in Graubünden this little structure. This was done by our MAS students. They did a lot of the development for this modular construction that ultimately looks like this. It consists of these volumetric modules that are generated algorithmically as line models. And then through Compass Timber, we're able to generate the beam information, including BTLX processings that we then post-process to fabricate on our CNC machine. Parallel to this, there's an augmented reality app that was developed that uses tracking of the individual elements through markers placed on the elements to ensure that they're placed in the correct position, correct orientation. For assembly, you can imagine with over 2,000 similar looking elements in this sort of chaotic assembly that you need some sort of guide like that, and printed paper plans are not going to cut it. So this turned out to be crucial to the process. This is showing sort of our three main, let's say, technologies that we implemented in this project. We have the CNC, we have the augmented reality, and then robotic fabrication. In this case, we leveraged the high precision of robots in sort of undefined geometric space in the workshop to place framing elements, and then humans who are good at adaptively assembling things that are maybe imprecise because they're made of a natural material like wood, do the infill between these two robotically placed frames. I don't know how my time is, so I might skip the videos. But we assembled in Zurich and then put them on trucks and sent them off to Graubünden to get lifted with a helicopter. Best day of my life. Standing there underneath, catching this thing by helicopter was quite the experience for me. And it now stands there. It should hopefully last a couple years. Get there while it lasts. go check it out. Questions? Oh, yeah. Or clap, I don't know. That's the end.